Is it possible to divide 1 millimeter by 10 divisions or 20 divisions or even 50 divisions and still be able to measure a length to that level of precision? For example, if you divide 1 millimeter by 2, you get 0.5 millimeters. You have seen some steel meter rules graduated in terms of 0.5 of a millimeter. That is possible, but I bet you have never seen a meter rule graduated using the smallest division of 0.1 of a millimeter. But there are some measuring instruments that can be able to enable us to measure to a level of precision of 0.1 of a millimeter. That means a millimeter has been divided into 10 divisions and we can accurately measure 0.1 of a millimeter. There are such apparatus or such instruments. One example is the Vernier calipers. In this video, I'm going to show you how we can divide that 1 millimeter into 10 divisions, 20 divisions, and even 50 divisions and be able to measure any length to that level of precision. And I'm going to start with a very simple scale. I've already talked about this scale where the level of precision is 0.01 of a centimeter. That is 0.1 millimeters. That means 1 millimeter has been divided into 10 divisions. You will agree with me that to mark such a scale on a meter rule or on a linear scale, it will not be possible because you will not even be able to see those smaller divisions. The smallest that maybe we can be able to see is 0.5 of a millimeter. That is 1 millimeter divided into 2. But when we divide 1 millimeter, a very tiny division, into 10 divisions or 20 divisions or even 50 divisions, it will not be meaningful to mark such a scale on such a linear scale because we won't be able to see it. But using a Vernier calipers, it enables us to do that. I've already talked about this particular scale, which has a least count of 0.01 of a centimeter or 0.1 of a millimeter. Maybe I will briefly review this so that we can use the same method to go over the other higher level precisions. And let's get right down into it. In order to get this kind of scale, or for you to be able to understand this, I've constructed this. I'm going to use this scale here. I have magnified it so that we can be able to understand. So from this point all the way to this point is 1 centimeter. And then that space has been divided into 10 equal divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in order to get the length of one division here, I divide 1 centimeter by 10 to get 0.1 of a centimeter. Or, 1 centimeter is 10 millimeters, and this is 1 millimeter. So if I divide that 10 millimeters by 10, I get 1 millimeter. And remember, 1 millimeter is the same as 0.1 centimeters. Now, I also have another scale just below here, exactly with the same spacing as the top scale. But I can be able to squeeze this scale like this. I've squeezed that scale in such a way that now it doesn't occupy the whole distance from here to here, but up to this mark here. In order to get the length of one division on this scale, which we refer to as the Vernier scale, what I do is this. I get the length occupied by these 10 divisions on the vernier scale, which happens to be 0.9 centimeters. How did I get 0.9 centimeters? I know that from here to here is 0.1, from here to here is 0.2, from here to here is 0.3 centimeters, and that means that from here all the way up to the 9th division, it is 0.9 centimeters. So I'm going to divide the length occupied by the 10 divisions on the vernier, which is 0.9 centimeters, by 10 divisions in order to get 0.09 centimeters. And let's do exactly that so that we can be able to see what is happening here. So this length from here all the way to this point is 0.9 centimeters. I divide that 0.9 centimeters by 10 divisions because there are 10 divisions here. I get 0.09 centimeters. That means that this length here from here all the way to here is 0.09 centimeters. You can see that it is smaller than the length of one division on the main scale. This is referred to as the main scale, and therefore in order to get this difference here, I get this length, which is 0.10. I subtract 0.09, and this is what gave us 0.01 of a centimeter. We refer to this as the least count. That is, this scale enables us to count in steps of 0.01. For example, 0.01, 0.02, 0.03 of a centimeter, and so forth. That is what least count means. Now, that means that this space here is equal to 0.01 centimeters. It means that I have successfully been able to divide this division here into 10 equal divisions. An equal division has got a value of 0.01 centimeters. Consider this. What is the length of one division on the main scale? 0.1 centimeters. How many divisions do I have on the vernier scale? 10 of them. And that gives me 0.01 centimeters. This is another way. This one is a quicker way of getting the value for the least count. I don't have to struggle to get the difference between the length of one division on the main scale and the length of one division on the vernier in order to get the value of the least count. It is a faster method of doing that. Although the previous method of getting the difference between the length of one division on the main scale and the length of one division on the vernier scale makes much more sense, because it explains step by step how the least count was obtained. So that is what we did with that scale. Now let me change that scale a little bit. By the way, before we go over to the next one, this is exactly what we have already talked about. Let's consider this scale here. You can see that this time the vernier scale has been divided into, you can see that here the vernier scale has been divided into 5 divisions. And before we even get the vernier scale, I need to shrink this like this until it comes there. And now I've got my vernier scale here, I've got the main scale here. How many divisions do I have on the vernier scale? I've got 5 divisions. 1, 2, 3, 4, 5. And what is the length occupied by the 5 divisions? 0.9 centimeters. So just like before, in order to get this length here, So in order to get this length here, that length, I'm going to get 0.9 centimeters. I divide by 5, and that is going to give me 0.18 centimeters. 0.18 centimeters. Now this time I don't get the length of one division on the main scale. I get the length of two divisions. Why is that? The number of divisions on the vernier scale must always be equal to the number of divisions on the main scale. Because if I did it the other way around, it would appear as if the length of one division on the vernier scale is greater than the length of one division on the main scale. That is not supposed to be the case. So what I will do, I will also make the number of divisions here to be equal to the number of divisions here, or better still, divide this one by 2 in order to make the number of divisions on the vernier scale to be 10, so that it can be equal to the number of divisions on the main scale, which is also 10. So when I come to this scale here, I'm going to find that this length here, all the way up to that point, is 0.2. So I'm going to get 0.20. I subtract 0.18 rather, and I'm going to get 0.02 centimeters. So this length here, I hope you can be able to see it clearly. That length here, which is the least count, is actually has got a value of 0.02 centimeters. This is a vernier calipers with a very low level of precision. The previous one has got a higher level of precision. This one has got a lower level of precision. But I'm just showing you how you can be able to construct your own scale with a particular level of precision. Now let's go on and see how we can get a vernier scale with a higher level of precision. And I'm going to get something like this. Now, the same scale from 0 to 1 centimeter, one division, 0.1 of a centimeter. Now this time, I'm going to use 20 divisions, because you can see that this lower scale here has got 20 divisions, just like the upper scale here. Just like the upper scale here, it has got 20 divisions. So what I will do, just like before, I'm going to shrink this by one division on the main scale. And that is what now I have. I have the vernier scale, this is the vernier scale, and this is the main scale. And you can obviously see that the length of one division on the main scale is longer than the length of one division on the vernier scale. How do I get the length of one division on the vernier scale? It's very easy. I'm just going to consider this. All the way from this point to this point is 1.9. The length of the 20 divisions on the vernier scale from here all the way to here occupy a distance of 1.9 centimeters, because this is 1.9 centimeters. And here I have 20 divisions. So remember, I want to find the length of one division on the vernier scale. So what do I get here? I divide 1.9 by 20. So 1.9 divided by 20, and I get 0.095. 0.095 centimeters. That is this length here. But one division on the main scale has a length of 0.1. So how do I get the difference between the two? I'm going to get 0.1 of a centimeter. I subtract 0.095, and this is what will give us 0.005 centimeters. And the level of precision has increased. You can see here that this scale allows me to read up to the third decimal of a centimeter. The previous one was allowing me to read up to the second decimal of a centimeter, although it was 0.01 of a centimeter. The least count was 0.01. In other words, I'm able to move in steps of 0.01. This one allows me to move in steps of 0.05. So I can get a reading like 0.05. The next one will be 0.10. The next one will be 0.15. The next one will be 0.20. The next one will be 0.025. You can see I'm reading the values or the difference between adjacent values which can be read accurately differ from each other by 0.005 of a centimeter. It's still higher level of precision than the previous one. So that is how, when you get a scale like this one, you don't need to worry about it. You just need to look at this difference between this number of divisions here and the same number of divisions up there. And remember, for you to get the correct value of the least count, you've got to ensure that the number of divisions on the main scale and the number of divisions on the vernier, they are the same. 20 divisions here all the way up to that point, and then 20 divisions here up to that point, and the difference between this length and this length is the length of one division on the main scale. That is the rule. Otherwise, if you don't follow that rule, you may get an impression that the length of one division on the vernier is bigger than the length of one division on the main scale, which won't make sense. I have had one of my viewers asking me that question, that it appears like on some scales the length of one division on the vernier scale is bigger than the length of one division on the main scale. That is how it appears like when you look at that scale. And let's go back to it so that you can be able to see what I'm talking about. This length here is obviously bigger than this length here. But remember, this one has been done like this in order to space out the divisions on the vernier to make it easier to see which division is going to coincide, which division on the vernier is going to align itself with that division on the main scale. That is why they have done that. Because if we are to have very many number of divisions here, then sometimes it becomes difficult to see which division is coinciding with which division. It does not mean just because it looks like this that one division on the vernier has got a bigger value than one division on the main scale. You've got to, first of all, ensure that the number of divisions on the main scale is equal to the number of divisions on the vernier, only that the same number of divisions on the vernier occupy a smaller length. Ensure that, and you will always find that one division on the vernier has got a smaller length than one division on the main scale. Let's proceed and we look at the final scale that I have for you here. And this scale is over here. This is the scale that I want us to look at. Let's look at it carefully. it ranges from 0 all the way to 5 centimeters. Now, how many divisions do we have there? From 0 to 1, I have 10 divisions. That means from 0 to 5 centimeters, there will be 50 divisions. I must have the same number of divisions on the vernier scale. But just like the previous one, I have reduced it to 25 because these are 1, 2, 3, 4, 5. Then I've got 1, 2, 3, 4, 5. I've reduced it to 25. Let's see what we get. We are going to say, or to do this, first of all, I'm going to shrink this until it just comes there, and you can see that the difference between the length of 50 divisions here and the length of the same number of divisions here, which is 50, only that I've reduced it to 5, is the difference is the length of one division on the main scale. And one division on the main scale is 1 millimeter, and 1 millimeter is 0.1 centimeters. So this is what we are going to do. Let me find out the length of one division on the vernier. And this is how we go about it. I'm going to get the length all the way from here all the way to this point, which will be 4.9. That length will be 4.9 centimeters. How many divisions do I have here? I have 25 divisions. Let's see what we get when we divide 4.9 by 25. 4.9 divided by 25, I'm going to get 0.096. 0.096 centimeters. That means this length here is 0.096. Now, what is the length of two divisions here? Because that is how we compare, in order to make sure that if I have 25 divisions here, I'm comparing it with the 25 divisions here, and now I have the length of that 25. What is that length? That length will be 0.2 centimeters. So in order to get the difference between these two lengths here and these two lengths here, I'm going to get 0.200 centimeters. I subtract 0.096 centimeters, and that is going to give me 0.04 centimeters. 0.04 centimeters. Now, this is the difference between two divisions here and two divisions here, which is going to give me that 0.004 centimeters. This is the value of the least count of this vernier scale. Let's see whether we get the same value when we use the other method that we just discovered. What was that method? You're going to get the length of one division here, which is 0.1 centimeters, and then divide it by the number of divisions you have here, which is 25. Which is 25. What do you get? So we get 0.1 divided by 25, and you get 0.04. 0.004 centimeters. And that is how you would get the value of the least count for this particular scale. So it goes in steps of 0.004. That is how you're going to count the values on that scale. So I hope I've been able to convince you that the length of one division on the Vernier scale is always smaller than the length of one division on the main scale. And the difference between the two gives us the value of the least count. I've gone ahead and shown you how to determine the value of the least count for any of these scales. All that you need to do is to ensure this. Check that the length of the Vernier scale and the length of the main scale, the difference between the two lengths is equal to one division on the main scale. Is equals to one division on the main scale. Once you have ensured that, then you get the number of divisions on the Vernier. You go up there, you divide the length of one division on the main scale by the number of divisions on the Vernier scale, and it will give you directly the value of the least count. And now you are on your way to reading that scale. In my next video, I'm going to show you now how you get specific readings when you're using these scales. The first one is pretty easy. This scale is quite easy to read. So I will spend least time there, but it's always good that you start with the easier one and then you go to the more complex scales. And maybe I'm going to use a real Vernier calipers this time so that we can zoom in into the scale and be able to get the specific readings. So in this video, I just want to recap a few points that we can be able to divide 1 millimeter into several divisions, even if they are 10, they are 20, they are 50 divisions, and we are able to read those values accurately when we mark that scale on the Vernier calipers. And that is all that we have for this video. In the next video, I'm going to look at how to read complex scales of the Vernier scale.